Perfect. So welcome back to almost the last lecture of electrodynamics. And today's lecture will be a follow-up of previous one, which was a magnetostatic. And indeed, we are going from, let's say, the Biot-Savart law, or let's say the differential equation that we had for the magnetic induction or magnetic flux density to materials, and we will solve a couple of problems with boundary conditions. So let's start with the problem that we had. I mean, the differential equation that we obtained was for the magnetic flux density. We got divergence of B equal to 0, and we got also curl of B equal to mu 0 J plus epsilon 0 time derivative of E, which for magnetostatic, which we assume that the divergence of J is equal to 0. So the current density, they are not function of time. Then we got the divergence of B equal to 0, and also curl of B equal to mu 0 J. And those were the expressions that we found. From the first equation, from divergence of B equal to 0, which is, there is no magnetic monopole in the world, I mean, that's the interpretation, we got that B is given by curl of A. And then we could substitute it inside of this equation. And what we got curl of A is equal to mu 0 J. All right. So by the way, the expressions that you see here, we derive them from Biot-Savart law and Faraday's law. So essentially, we did really the calculation and we obtained these expressions. Now what I will do, I will go from a different perspective. So now we know that the divergence of B is equal to 0 and curl of B is equal to mu 0 J. And we can do the expansion. And what we can get is that using the backup law, we'll get Laplacian. Oh, sorry. That will be back. Divergence of A minus cap, which is Laplacian of A, equal to mu 0 J. And we choose divergence of A equal to 0, which we call it Coulomb gauge. And from here, we got minus Laplacian of A is equal to mu 0 J, or Laplacian of A is equal to minus mu 0 J. And remember, that's a free current density. All right, so we got this expression. And remember, that's a vector relation or vector differential equation. Because we do have, for example, in the Cartesian coordinate, we do have this minus mu 0 Jx and Laplacian of Ay, the same scenario, mu 0 Jy, Laplacian of Az is equal to minus mu 0 Jz. Okay, so remember, that's how the current along X, Y, and Z, they will be creating Ax, Ay, and Az. Okay. No questions so far? Okay. So as soon as we know the Laplacian, and we know that the current, I mean, essentially, if you look at the geometry, we do have a certain, let's say, current in a space, and then we are calculating the vector potential here. At the point of observation, and from the vector potential, also we are calculating B at this point. So we can assume that those currents, they are localized in space, and we have the ability, it does not extend to the entire space. Then it is a Laplace equation that we do have, and we know that the surface can go to infinity. And what we can do, we can use the Gauss theorem and finding out the explicit expression for vector potential. How can we do that? If you remember, let me think about the Gauss theorem. So we had the divergence. Yes, it was a divergence of psi gradient of phi, which was the product of the inner product of the two gradients plus psi Laplacian of phi, and we can write that also for phi gradient of psi, and then we got the same expression. Then we can subtract them together. Then we get divergence of psi gradient of phi minus phi gradient of psi equal to psi Laplacian of phi minus phi Laplacian of psi. Then we can do the integral on a space and in terms of volume, then bringing that to the surface, that will give us psi into phi minus phi gradient of psi dot d, let's say n d sigma is equal to integral of psi Laplacian of phi minus phi Laplacian of psi d volume. Okay, so that was the green term, the second green term that we obtained. And remember that here psi, phi, they are scalar quantity. Okay. Indeed, in the past, what we have done, we assume that psi can be 1 divided by x minus x prime. And we know that the Laplacian of psi is given by minus 4 pi delta of x minus x prime. Okay. And in order to clarify this, that can be on a prime one as well. So I mean, at the end we can just modify that. So and we introduce a green one of the green functions, and the integral was on a volume, and that integral was on a surface, and we brought this to the surface, and we defined that if we are dealing with the Dirichlet, or we are dealing with the Neumann boundary condition, and we solved the problem entirely, right? So is that clear for you guys? Okay, perfect. So it was just simple review. Remember, whenever we had a localized current or localized charge distribution, the first term, that one, since that was localized, it means that psi gradient of phi, because psi was 1 divided by x minus x prime, and phi, which was the scalar potential, all of them, they were localized for the charge distribution. Then the rate that we had for psi gradient of phi, phi gradient of psi, it was way lower than r square. Way lower than r square. So it was going to be 1 divided by r power of 3. So essentially, as soon as you had the charge to be localized, then that integral is going to be 0. So the left integral was 0. And we ended up with this expression, which was integral of psi, Laplacian of phi, minus phi, Laplacian of psi, d3x prime equal to 0. Okay? So indeed, I mean, for simplicity, we can just add a prime index here to tell that the derivative is on the prime and integral also is on prime. So we obtain that integral of psi, which is a function of x prime, Laplacian prime of phi minus phi Laplacian prime of psi, d3x prime is equal to 0. So, and then we replace psi by 1 divided by x minus x prime. And on the other side also, Laplacian prime of phi was minus rho divided by epsilon 0, and rho was a function of x prime as well. Do you remember that, right? And when we substituted here, we got integral of 1 divided by x minus x prime, and that was minus rho of x prime divided by epsilon 0, and then the other term was minus phi of x prime. Then we had Laplacian of these, which was minus 4 pi delta of x minus x prime. And then we had d3x prime equal to 0. So we knew that the integral of the second term will be equal to 4 pi phi of x. And then we obtain integral of minus rho of x prime d3x prime divided by x minus x prime plus 4 pi, there is 1 divided by epsilon 0 here, phi of x is equal to 0. And from here, we obtain that phi of x is equal to 1 divided by 4 pi epsilon 0 integral of rho of x prime d3 of x prime divided by x minus x prime. So we obtained this based on the fact that there were extra term here due to the surface or due to the boundary. But as soon as the charge is localized and the boundary can be extended to infinity, then that was the explicit expression that we had. All right? That was what we had in electrostatic. Now remember that for magnetostatic, we are facing similar problem. What we have is Laplacian of A is equal to minus mu 0 J. Okay? But instead of a scalar quantity, we are dealing with a vector quantity. So what does it mean that for the AX, we have Laplacian of AX minus mu 0 JX. All right, so this is very similar to the expression that we had previously, which was Laplacian of phi equal to rho minus rho divided by epsilon 0. As soon as the charge was, they were localized, what was the solution to this problem? Using the Green theorem, that was the solution that we had, because we could go to infinity. Here, the same situation. As soon as the charge and the current densities are localized within certain volume, then the solution that we are expecting for AX will be AX of X will be exactly in the same way, 1 divided by 4 pi integral of mu 0 Jx of x prime d3 of x prime divided by x minus x prime. What I have done, I just look at the expression that I had for the potential, and just I replace rho of x prime with mu 0 jx. True? Is that clear? Okay, perfect. So for ax of x, I got mu 0 divided by 4 pi integral of jx of x prime d3 x prime divided by x minus x prime. The same expression holds for ay, az. So therefore, what I will get that a y of x also is equal to mu 0 divided by 4 pi integral of jy of x prime divided by x minus x prime d3 x prime, and a z of x prime, sorry, x is equal to mu 0 divided by 4 pi integral of jz of x prime d3 of x prime divided by x minus x prime. These are the three components of the A. You can combine them together, and what you will get A of x is equal to mu 0 divided by 4 pi integral of j of x prime divided by x minus x prime d3 of x prime. How did we obtain this, by the way, guys? Remember the condition that we obtained, this expression. Edith? Do you have any comment on that? No? So what was the condition that we obtained these expressions, guys?
That it equals 0.
What?
No, that it equals 0.
What is equal to 0?
Oh, sorry, when you take the Laplacian.
When you take the surface to infinity, right? And then you assume that the charges are localized. As soon as we have that term, because if we look at that term, that is true for ax and ay and az, and we assume that the rate that you do have is way lower than the surface rate, essentially. So if you bring it to infinity, then that term will be essentially 0. Is that correct? Gavin? Yeah. So if it's not 0, if the charges or you have a different boundary condition, what do you expect here? Any thoughts?
We need to use the second green, starting from that very first expression and write all the different integrals. And
so you need to have, I'm writing that down, minus, let me see, it was minus, yes, psi, which is 1 divided, and let's say I will call it green, of x and x prime. Okay, then we had the gradient, which is the n prime of the potential, which is a, remember, of x prime, then minus a of x prime, then n prime of g of x and x prime, d3 of x prime, sorry, d2 of x prime, and that's on the surface. So whenever it is localized, is that correct, guys? By the way, let me see. Yes. Yeah. So when the charges on, or you have a boundary condition which does not extend to infinity, then you have the surface contribution from them, which means that depending on which boundary condition that you choose, either the derivative of the potential will play a role, or the derivative of the green function play a role. Or if I want to say in this way, either the potential should be known at the surface, or the derivative of the potential should be known at the surface. Okay, so this is something that you should also consider that. People, they don't really do a lot about the magnetostatic, because you will see it in maybe in about half an hour that people, they don't usually deal with A, okay? Is that clear? But remember, what you learn in the first two chapters can apply here. And now exactly is the same green theorem that you do have applies here, but instead of a scalar, you are dealing with a vector, okay? Or you are dealing with three scalars component, okay? Is that clear?
So in this case, do we still consider things like the Dirichlet and the Neumann conditions?
Exactly, exactly. That defines which G do you consider. Do you consider the Dirichlet? Then you are dealing with A. Do you consider Neumann? You are dealing with the derivative of A. Exactly the same way. Remember, A is look like three scalars that you do have, and that's the story. It's getting a little bit more complicated in terms of computation, but the same mathematics can apply. Okay, good. So indeed, I'm assuming that I have, as I said, I have a charge distribution which is localized, so it doesn't extend to infinity. And I'm looking at the region outside of that, and if that's a J of X prime, then clearly here, if that is X prime and that is X, then for this point of observation, the potential scale, vector potential is given by mu0 divided by 4 pi integral of J of X prime divided by X minus X prime, E3 of X prime. Beautiful. And now we would like to understand what's going on with the contribution of those currents that we do have here. What is happening with the contribution there? Exactly look like the scalar potential. If you remember, for the scalar potential, we assume that we have a charge distribution, and then we look at far field, and we look at the contribution from each of them. And that was the multiple expansions that we had at that time. The same way, so 1 divided by X minus X prime, which is that distance here is X minus X prime. We assume that is way, way greater than X prime. Okay? So X is way, way greater than X prime. Or you can assume that X prime is way, way greater than the X, depending on what you consider. In any case, one of them is much greater than the other. Okay? Then what we can do?
Expand it.
Exactly, we can do the expansion. Which coordinate do you prefer to do?
Spherical.
Spherical. Let's do that. What is 1 divided by X minus X prime? Expanding is spherical.
1 divided by sigma of 1 divided by 4 pi.
It was 1 divided by r greater
Yeah.
summation
Oh, yeah, sorry.
of L from 0 to infinity of r smaller divided by I greater power of L, if you
Yes.
remember that. And then we had a PL of cosine of theta or gamma, let's write it gamma. And then PL of cosine of gamma was expanded in terms of addition theorem. Do you remember that?
Yes.
PL was in terms of addition theorem. And that was, I think, someone may help me. It was going
2
from,
by 11 cabinet.
it was YLM theta and phi prime star YLM of theta and phi. There were a coefficient of 1 divided by 2L plus 1, something like that. Yeah, can someone check the addition theorem? I can check it out as well. Addition. Sorry, guys. It will be. I think I cannot find it, but I think that should be something like that, 4 pi, something like this, if I'm not mistaken. So that will be 4 pi divided by r greater. Then we have two summations of, someone can check it, please. I'm sure that they exist inside of your book. M from minus L to L. Then we do have 1 divided by 2L plus 1. Then we do have r smaller, r greater power of L. And then we do have YLM of theta prime and phi prime star and YLM of theta and
It is
Can
4
you-
pi. I just found it in the textbook.
Yeah,
There's a 4 pi?
Yeah.
Okay. Is that expression correct?
Yeah.
Okay, perfect. Thank you very much. So then we do have A of x is equal to mu 0. 4 pi goes away because it is in the denominator. Then we do have 1 divided by r greater. Then I have to be careful. Let's write it in this way. Integral of d3x prime 1 divided by r greater summation of L from 0 to infinity, summation of M from minus L to L, 1 divided by 2L plus 1, R smaller, R greater power of L, YLM theta prime and phi prime, YLM of theta and phi. Then we do have the current, which is J of x prime. Okay. Clear? Beautiful. So that will be mu 0 summation of L from 0 to infinity, summation on M. Then that will be integral of, oh, I can write that 1 divided by 2L plus 1. And then I will write YLM theta and phi. And then we do have integral of d3 x prime. Then we do have J of x prime we do have 1 divided by r greater, r smaller than r greater power of L, and YLM theta prime and phi prime star. What I have done, I'm just taking the argument, they are independent of theta prime, phi prime, and r prime outside. So that is essentially the multiple expansions that we do have. For simplicity, I assume that the distance that I'm looking at it is far away. So the r smaller will be r prime, and r greater will be the distance, which is r. So let's go and do that expansions. That will be mu 0. Again, the summation on L, the summation on M. And then we do have 1 divided by 2L plus 1. And since I assume that r greater is r and r smaller is r prime, then that will be 1 divided by r power of L plus 1. Then YLM, oh, I can write that, YLM here, theta and phi. Then I do have integral d3 of x prime. If you recall this, that will be, it will be r prime, dr prime, d of cosine of theta prime, d of phi prime. That is the element of the volume that we do have. Okay. Good. Okay. Then we do have r prime power of L, which is coming from that term. And then we do have YLM star of theta prime and phi prime. And then we have J of x prime, which is r prime, phi prime, theta prime and phi prime. Good. Yes. Tarek. You have to close the mic of another one as well. So the mic and speaker of both are on.
Should it be r prime squared though? Sorry.
Pardon?
Should it be r prime squared though? Because it's r squared sine theta.
Yes, that will be r prime. Yes, thank you.
Yeah, okay.
Good, okay, thank you. The dimension should be r power of 3, right? Yes, thank you. That's correct. So this is what we do, and we obtain that. So that will be essentially r prime power of L plus 2, dr prime, and then we have d of cosine of theta prime, d phi prime. And remember, r is changing from 0 to infinity. Yeah, and theta prime is changing from since d cosine of theta we are dealing, it's -1 to +1, and d phi is changing from 0 to pi. And then what we have is j. Remember, when I write j as a vector, is jx, jy, and jz. And then it will be j of r prime, phi, theta prime, and phi prime. YLM of 0 and theta prime and phi prime. Good. Now, definitely we can expand L's. So if is L equal to 1, or L equal, the first term is L equal to 0. So then it means that M also is 0. Good. Do you agree with me, guys? The first term is L equal to 0. Then M, which is changing from minus to L is 0 again. So that will be mu 0, 1 divided by 1, y0, 0, theta and phi, and then that will be r power of 1. Then that integral, what we have is integral of 3 r prime power of 2 dr prime d cosine of theta prime d phi prime, and then we have a j of r prime phi theta prime and phi prime, and l and m also they are 0. And do you remember that ylm, when l and m they are 0, is simply 1 divided by 4 pi square root? Okay, you remember that? You agree? Fantastic. So then that will end up with mu 0, 1 divided, 1 divided by 4 pi, which will be 4 pi is coming from the other side. It will be 1 divided by r. And then we are dealing with this interesting integral, which I will write it as again as a d3 x prime of j of x prime. Good? Because the ylm goes there, and it is essentially the same expression that we do. What is this value, guys? Mathematically, I can prove it to you, but I want you to think and tell me intuitively what is happening.
Like the total flux on the volume.
Is on the value.
Yes.
What is going on with the total current
Charge.
density?
Yeah.
What?
Yeah, like electric charge.
Electric charge, okay. Any thoughts? Let's prove this first.
The overall current going through the wire.
Remember, what is the integral?
So isn't it just I, like capital I?
This is a vector. What you are telling me is I. Can it be? No, because you have to do a dot product in order to get the I. But you were close. You were really, really close. Okay, let's do and prove that mathematically. Let's do the calculation of divergence of two well-behaved function of f and g and a current j. Since I'm doing the dots, let's do that, assuming that j is a function of x prime, f also is a function of x prime, g also is a function of x prime. Okay, what is this value? Is a dot is a divergence of two scalar functions and one vector function. So you can do the expansion, and essentially that will be the derivative of I of derivative prime of I f g j I. Then that is derivative with respect to I of f multiplied by g j I plus f derivative with respect to I of g multiplied by ji, and then f g derivative with respect to I of ji. So if you write it in the differential form, that is g gradient prime of f dot of j plus f gradient prime of g dot product with j plus f g divergence of j of x prime, of course. Do you agree? Is that right? Good. Okay. So now multiply by d3 of x prime. Do the integral on the volume. Using the Gauss theorem, the left side will become integral on the surface. So it will be f g j dot n prime d2 of x prime on the surface of the volume. The right hand side becomes 3 integral on the volume. So it will be g divergence, sorry. F dot j. Remember, that's a function of x prime plus f dot j plus f g. Okay. Any questions? So far, so good, right? Okay. So if the function of f, function of x, g, and the j, they are well-behaved function and they are localized in space. This is what the assumption that we had, essentially. Then the integral on the surface, when you extend the surface to infinity, again, with the same theorem, the same assumption that we had, that will be 0. Okay? So that will be equal to integral of v for g. I mean, I'm writing that again. F dot j plus f gradient prime of g d3 x prime. Do you agree? Nazanin? Okay. So that's, I have not done any assumption. The only assumption that I had that f and g, they are well-behaved function, that you can take the derivatives, any arbitrary derivative that you want. And at the end, I assume that the j is localized. This is the only assumption that I had, and I got that expression. Now assume that g is equal to 1 and f is equal to xi. Okay. And see what we will get from this expression. All right. Good. Okay. And for sure, I know that the divergence of J also is equal to 0 because it's a magnetostatic. So replace it here. I will get integral of 1 multiplied by gradient prime of xi dot j of x prime plus xi gradient prime of 1 dot j plus xi multiplied by 1 divergence of j of x prime d3 of x prime. Do you agree? What is this term? Laptop
Is it 0?
is a 0. What about the second term?
Again, 0.
0. Perfect. What about this one? Can you tell me? Integral of gradient prime of xi dot j of x prime d 3x prime. Any idea?
Is it just jx?
Exactly. It is integral of j of x prime d3x prime, which the right side, left side was 0. Okay. Take that derivative that is giving you the vectors that will give you the I component of the vector. You can do it for first component. You can do it for the. I see Nazanin's face, which is look like a big question for me. So assuming that I is equal to 1.
No,
So
I have a
what you will
question.
get?
That's like x to power of I or x prime? That's
No,
why
it's-
I'm confused.
xi is the component.
Oh, so I thought it's x to the power of I.
No,
So I'm
is
all
the
good.
component.
No, all good. Now
Good.
it's
Okay, good. So is that clear now? Because that will give you the EI, essentially, which is a unit vector along the I direction, dot JX, that will give you the entire days, will give you JI of X prime, right? So I can be 1, 2, and 3. So indeed, from this, we will get that the entire vector of J integral will be equal to 0.
sorry. Also, it's x prime I, right? So it's
Oh, yes, yes, that's X
yeah.
prime. Yeah,
Thanks.
thank you. Yeah, that's X prime. Yeah, good. Clear? So, integral of current density in the entire space is equal to 0 if the divergence of J is equal to 0, which sounds correct, because it means that the current density starts from somewhere and ended up in the same place. So if you integrate on the entire space, there is no way that you are creating a new current unless the charge densities are a function of time. If the charge densities are changing in time, then the current is changing as well. Then this integral is not equal to 0. Okay? So what I want to tell you, going back to, I did this calculation because I want to look at the 0, L equal to 0 contribution to the potential when we do the multiple expansion. And what we found out that A of X, and if we look at the L equal to 0 term, that will be proportional to integral of J of X prime, D3 of X prime, and that is equal to 0. So whenever we have this potential, which is mu0 divided by 4 pi integral of J of X prime, D3 of X prime divided by X minus X prime, and we do the multiple expansion, there is no contribution from 1 divided by R. The contribution starts from L equal to 1, which goes to be 1 divided by R power of 2. Okay? Is that clear? So let's look at the expansion. Maybe I've done some mistakes, but if it's R power of L plus 1, L equal to 1 will be 1 divided by R. L equal to, L equal to 0 will be 1 divided by R, and L equal to 1 will be 1 divided by R power of 2. Okay? So it seems that there is no monopole contribution. Monopole contribution is 0. Does not look like the scalar potential with the monopole contribution exists and will give you the total charge divided by R. Here, no, it starts from the second term, which is a dipole contribution. Okay, So this is the huge difference that you do have between electric field and magnetic field. And remember, whatever we talk, I mean, in electric field, when we talk about the potential, scalar potential, and here for magnetic flux density, we are talking about A, which is a vector potential. And doing the expansion here, we do get Q divided by R, and then we got X dot P divided by R power of 3, which essentially is, by the way, remember that is R power of 2 because there is an X term on the R. And plus the other terms, which is the quadrupole term and etc. But here in the vector potential, it seems that that term is 0, and we are starting from the second term, which is 1 divided by R power of 2. And we call these magnetic dipole term. Okay? In the spherical coordinate, we have to assume L equal to 1. Then how many terms do we have? M equal to 1, M equal to 0, or M equal to -1. And we can do the expansions for all of them, okay? And we can do the calculation. For that specific case, if you want to solve this, you need to go back to this integral that I introduced here. And from that integral, you can do the calculation. However, in order, I mean, you know that spherical coordinate always gets you to complicated scenarios that you don't have any good feeling about the expansions. Let's do that in the Cartesian coordinate and have a little bit of better feeling. Is that clear, by the way, guys? Good? Okay, perfect. So look at the AX 1 divided, mu0 divided by 4 pi. Did I say yes? Okay. Integral of j of x prime d3 of x prime. Quickly, I will write the expansion. So 1 divided by x minus x prime, as I say, that you can do the expansion in any coordinate. And let's do that for far distances and do it in the Cartesian coordinate. If you do it in the Cartesian coordinate, that will be first approximation 1 divided by r. The second approximation will be x dot x prime divided by r power of 3. And the other term will be higher order, the expansions. We can use the Taylor expansion that previously we introduced. So essentially that will be summation of x prime dot nabla divided by n factorial, and that is power of n. And you can do the expansions on any function of f that you had. You can do that, by the way, but and n is changing from 0 to infinity. Is that clear? Good. Now replacing here, we will get mu0 divided by 4 pi. I don't spend too much time. Now it will be integral of j of x prime divided by r d3 of x prime. Then I have a second term, which will be 1 divided by r power of 3, integral of, maybe I have to do something else. That will be 1 divided by r integral of j of x prime, d3 of x prime, plus x dot r power of 3 dot integral of x prime, j of x prime, d3 of x prime, plus the other term. Clear? Good. Melika, do you have a question? Okay, perfect. What is the first term? We just proved is 0. Is 0. So doesn't matter, is it spherical coordinates, cylindrical coordinate, or Cartesian coordinate, always that term, the monopole term is 0. What about this term? We have to do the calculation now. Integral of xi or x prime I, j of x prime, d3 of x prime. Okay. Or let's write it in this way. What we are doing as a calculation now is this. It sounds a little bit strange to you, right? Because it's two vectors together. But remember, there is a dot product between that integral and the x vector here. Okay? Or if you want, you can just write it in this way. Just remember. So it means that it has three terms. Integral of x, x prime, j of x prime, d3x prime, plus y integral of y prime, j of x prime, d3x prime, plus z integral of z prime, j of x prime, d3 of x prime. So essentially, that is what we are dealing with. Or for short, I will write it in this way: integral of xi, integral. Another, this is x, the I component. Okay, x prime I, j of x prime, d3 of x prime. I is changing from 1 to 3. Good. So now I am not dealing with integral of the current density in the entire of the space. I am dealing with the integral of x I, which is x prime or y prime or z prime, multiplied by the current density in the entire of the space. So it seems that I'm looking for a moment of it. So another higher expansion of these. So using the same expression that we had, which was the same integral that we had, which was integral of f gradient prime of g dot j plus g gradient prime of f dot g, sorry, j, f g divergence of j of x prime in the entire of the space, which was 0 for localized charges. Remember that we just proved this. Now for this integral, we assume that f is equal to x prime I and g is equal to x prime j. And divergence of j is equal to 0. So the first term will be, the last term will be 0 because that's what we are dealing with. And from the first term, what we will get, the first and second term, we will get integral of x prime I, then gradient prime of g, which is xj, that will give you the j component of j, so it will be j. Do you agree on that? Or should I prove that? Okay. Of x prime plus g, which is x prime j, gradient prime of f, which will give you e prime I, dot j, which will give you j of I of x prime, d3 of x prime. Agreed? That is equal to 0. Beautiful. So what does it mean? That integral of x prime I j of x prime d3x prime is equal to minus integral of x prime j of x prime d3x prime. Let me write it in a different form, guys. It means that if you have integral of x prime jy of x prime d3 x prime or d3 volume is equal to minus integral of y prime jy of x prime d3 x prime. Okay. That's a property that the current density has. Clear? Beautiful. So, I'm going back to that expression that we had, which is this. Good. I'm going with that expression, and I'm applying the following relation that I have here. So that will be equal x dot integral of x prime j of x prime d3 of x prime equal to, which is equal to summation of I, which is changing from 1 to 3 of xi integral of x prime I j of x prime d3 of x prime. So indeed, this is another summation on, because the j is a vector. So essentially you have I component, j component, and z, x component, y component, and z component. So essentially the I component of the j component of this will be the j component of that. That will be summation of I from 1 to 3 of xi integral of x prime I j of x prime d3 of x prime. So I will write that as 1/2 of I from 1 to 3 of xi. Then I have two terms here, integral of x prime I j of x prime d3 x prime plus the same x prime I j x prime d3 of x prime. Clear? I just write it as twice of these, okay? One is, these two, they're identical. Why I'm doing that? Because I want to make an antisymmetric state. Here, antisymmetric expression. So look at that, this one, and look at that expression. Can I replace it with a negative sign? Just swapping I and j index together. Let's do that. So that will be 1/2 of summation of I from 1 to 3 of xi. That one will be integral of x prime j of x prime d3 x prime. Or I can also swap when we say having the same expression for it's the same integral for them with the negative sign. Let me add a negative sign here. Plus x prime I j of x prime d3 of x prime. Good. All right, fantastic. So I will write that as minus 1/2 of summation I from 1 to 3 xi integral of x prime I swap them together. Should I write that way? No, I will write it in this way. Okay. I will take away the I sign, so I will write it in this way. J I of x prime minus x prime I j of x prime dt of x prime. Good. What is this, guys? Is the cross product of j and x, right? So that is x cross j. All right. Do you agree on that? And what about this one? So if you do the expansions, that you will get -1/2 of x cross integral of x prime cross j of x prime d3 of x prime. So the entire of this, it can be written in this way because you know that there's a cross product, and then you are doing the summation. Then if you look at the property, the antisymmetric property of epsilon ijk, which is a Levi-Cheeta tensor, then you will get that expression. Okay. So we got x dot integral of x prime j of x prime d3 of x prime, which we proved that is -1/2 of x cross integral of x prime cross j of x prime d3 of x prime. Good. So for dipole moment, for dipole approximation, essentially, because the first term, which was the monopole approximation or dipole term, what we have that the potential of x is proportional, or is approximately is given by mu0 divided by 4 pi 1 divided by r power of 3, and then we have -1/2 of x cross integral of x prime cross j of x prime d3 of x prime. Good. And remember, the first term was 0. The monopole term was 0, and that's a dipole term. This is the property of the material and defined based on the geometry. We call these, with the coefficient of 1/2, we call that magnetic dipole moment. Okay. I think if I want to use the definition that your book they use, it is mu0 divided by 4 pi 1 divided by 3 r power of 3. Then we had minus x cross, I call this m, which the minus sign will allow us to swap m and x. I will get that expression, which m, we define it as a 1/2 of integral of x prime cross j of x prime d3 of x prime. Okay, and we call these magnetic dipole moment. Okay. Is that clear? So again, I'm looking at the phi, which was the electric scalar potential, which the first term was Q, assume that we have 1 divided by 4 pi epsilon 0, then we had Q divided by R, and then what we had P dot X divided by R power of 3 plus the other terms. Do you remember? Here, the scalar and the vector potential that we do have is given by mu 0 divided by 4 pi. That term is 0 divided by R. The second term is given by M cross X divided by R power of 3 plus the other term. Fantastic. Okay. I will let you have some rest and coming back, and then we'll talk about the physics of magnetic dipole moment. All right. So have about 15 minutes of rest, and then I will see you at 4:05. Okay. So welcome back. Excuse me. Let's try to understand the meaning of those terms. So, as we discussed, that scalar potential was given in terms of multiple expansion, which was a monopole, dipole, quadrupole, etc. And for the vector potential, the same story happens, but the monopole term is essentially 0, and the expansion starts from a dipole term. And in order to find electric field, you have to take the gradient. Electrostatic and magnetostatic, we are talking about these. You have to take the gradient of phi. And for magnetic flux density, you have to take the curve of A. So that was the mechanism. And then from this, you can calculate what's going on with the forces. So let's look at the magnetic dipole moment M, which was given by 1/2 of integral of x prime cross j of x prime d3 of x prime. Assuming that, of course, these are very, very general expression, and j of x prime is a current density in the space in the volume. But whenever we have a loop of current in a plane, so assuming that, for example, the current is on the edges of these plates, which is located on a surface, for example, like this. So assuming that I have certain loop and it's closing X coming back, and then I have a certain current here, which is I, and then the element of the wire, which is DL or DX prime. Then previously we discussed that these can be replaced simply by IDL, so that will be replaced by 1/2 of integral of x prime cross dx prime multiplied by I. Okay, you remember that. So we previously say that J dV can be replaced by I dl, or can be replaced by K d sigma, which is the three forms that you may see: current density in a volume, or the current which is on a line, or can be current on the surface. So these are the three forms. So, and for this specific geometry, that will be 1/2 of I integral of x prime cross dx prime. All right, or simply I can write I multiplied by 1/2 of integral of x prime cross dx prime. And when we do this, that is on the whole space, and whole space for us is, it will be the whole loop, essentially. So that will be the whole loop that the current exists there. Good? Okay. What is x prime cross dx prime? You're muted, guys. Remember, that is x prime. That is dx prime, right? The cross product between these two will be something like that. So what is happening with x prime cross dx prime will be x times dx times the sign between the two. So that will be essentially the entire of that surface that you have. Do you remember that? So if you have a two vectors of A and vector of B, then A cross B was the surface generated by these two vectors. All right. And what about 1/2 of these? 1/2 of this is essentially that small shaded area here by this triangular. So 1/2 of x cross dx prime, which if you assume that that's x prime and that is dx prime, essentially that shows us that shaded area here. And if you do the integration on the entire of these dx prime, that will be the entire of the surface that you see here. Or I can write it in a different way. I can write it as S multiplied by n vector, which n is the vector generated by x prime cross dx prime, which is orthogonal to the both of them. All right. It's orthogonal to that surface. So if that is in the plane of x and y, definitely that vector will be z. So essentially, magnetic dipole moment will be I multiplied by the surface multiplied by the unit along the surface. Okay. Or let's say, let's go with n. SI n vector. Good. For a circle of radius I, radius a, that will be pi a square I n hat. And that was what we got it from the previous lecture for a loop of a current, right? If you had the loop of current, everything was expanding in terms of that, which was a magnetic dipole moment, indeed. Is that clear? So if we do have a loop of, let's say, a loop of a current like this in a given plane of x and y, the radius is a, that is in a plane of x and y. Assume that x is this one and y is this one, and that's that. Then far away from this place, far away from the circle, what we get as a vector potential will be given by mu0 divided by 4 pi, excuse me. And then we do have m cross x divided by r power of 3, which indeed will be mu0, 4 pi. And we already calculated what's the magnetic dipole moment for this, which is pi a square I, which if the current here is I, and along z direction, which is z hat, cross x divided by r power of 3. And if you assume that that's x, and that is n, which is along z hat, that angle is theta, then that will be mu0 divided by 4 pi, pi a square I, z cross x, that will be r sine of theta divided by r power of 3, which is mu0, 4 pi. And by the way, that's approximation. Don't forget that. That will be mu0 pi a square I sine of theta divided by r power of 2. That was the vector potential for a loop of current in a given plane far away from that place, okay, within the approximation that we had. How do we calculate the magnetic field or magnetic flux density? B is given by curl of A, and indeed that will be curl of mu0 divided by 4 pi of m cross x divided by r power of 3. So that will be mu0 divided by 4 pi. And remember that m is constant, is independent of the x coordinate, I mean x vector. So that will be curl of m cross x divided by r power of 3. And if you do the mathematics simply, you will get mu0 divided by 4 pi. Then I think you get something like that, which is 3x x dot m divided by r power of 5 minus m divided by r power of 5, which is magnetic flux density for a dipole, for a magnetic dipole, or essentially for a loop of a current that you can apply and you can obtain the expression. Is that clear? Good. How do we create currents, guys? Now, look, we did the general expression. We say that they are localized. Let's do the multiple expansions. And from the multiple expansions, we get this, okay? And then we came out with the lower level, which is what is happening with the loop of a current. If you have a loop of a current given in a plane, that is the vector potential, and that is the magnetic induction. And now we go a level also down, and we look at the individual atoms or electrons. So how do we create currents? Can you tell us, guys?
Is it like by applying a difference in potential so that they start moving from like lower potential to higher potential, something like
By
that?
moving the charges.
Yes.
So if you have a charge of Q moving around with the velocity of V, you are creating a current, right? Is that true? What is the current density? that for this charge we obtain in space. Exactly, is a Q multiplied by V, where? For that specific one, right? So let's go with J small, just to make clear that is we are talking about that specific charge. So if you have a set of charges moving in space with velocity of I in a position of xi as well, so at the end of the day, what you will get, the charge density, the current density essentially will be given by the summation of all of those movements of the charges that you do have, which is a qi times vi times the delta of x minus xi. Agreed? Okay, perfect. So that is essentially what we are expecting for, these are how we expect that the current will be created in the space by moving the charges, as Nazari mentioned. So if we have these charges which they are moving, and usually those charges they are moving in materials, they are electrons because they have less mass, and the mass that we have is way smaller than the mass of proton. Okay. So those are what we expect that they are moving around. And remember that that's not really the physical movement, because it's not one charge that is moving around. It's that one of those, let's say, electrons are pushing in, and some electrons are moving out from an environment. So we do have a drift velocity, which essentially we have to consider. Okay, fantastic. So this is the charge density, the current density that we do have. So if you have this current density, then I'm expecting, due to this movement of the charges, to create certain dipole moments, right? So which is the first approximation that we are seeing. We are not expecting to see monopole, but we are expecting to see the dipole term, which is given by 1/2 of x. 1/2 of x prime cross j of x prime, d3 of x prime. So replacing here, we get 1/2 of integral of x prime cross the summation of I from 1 to n of qi vi delta of x minus xi, d3 of xi. So that will be essentially the summation of I from 1 to n, and that will be indeed qi xi, which will be replaced, multiplied by vi. Do you agree? Essentially, x prime will be replaced by xi. That will be replaced by this. Are we good? Okay, perfect. Can I multiply both sides by mi? So I will get I from 1 to n. Then I will get 1 divided by mi qi. Oh, let's write it in this way. qi. Then I will get xi cross mi vi. What is mi vi? M is mass of that charge. So what is MIVI? Exactly. Yeah.
The momentum of
Yeah,
particle.
exactly. So then you will get I from 1 to n, qi divided by mi, xi multiplied by momentum of that particle. What is x cross momentum? What is this then? X cross P? Guys?
Angular momentum.
Angular momentum. It is summation of I from 1 to n, qi, mi, li, which is angular momentum of that specific charged particle. Which is moving with velocity of vi. Okay. So what is happening? It seems that if you have moving charges around, then you have a coordinate, you look at the distance between them, and then you calculate what is going on with x cross p. And then due to this x cross p, you will get a dipole moment. That is very, very interesting. So essentially, dipole moment is associated to the angular momentum of the charges in a given plane or in given space. And those angular momentums that are ending up together. Okay? So assuming that all of those charges, they are electrons, because we just discussed that. So we say that electrons, they have less mass, so they are easily moving around. It's way easier. So all of those charges are electrons. So it means that qi divided by mi, they are electrons with the mass of m. So that summation will be simplified by, oh, by the way, there is 1/2, which I missed in all of the calculation, which is very important. I was very surprised, okay? That will be 1 divided by 2 of E divided by M, summation of Li. I is from 1 to n. So if you have a bunch of electrons of n, and then they are moving in space, indeed, the dipole moment associated to them, it will be given by 1 divided by 2, E divided by M, and the summation of all angular momentums of those electrons together, which I will call that total angular momentum of LT, which is the total angular momentum of those electrons that they are moving around. So it will be 1, 2 of E divided by M of angular momentum of T. So remember, that's the dipole moment of bunch of electrons which they are moving in space with total angular momentum of LT. Okay, perfect. It turns out that that is almost close to the reality. And the only thing that is needed to be true is that you need a coefficient which we call a G factor here. So G factor for electrons will be, the dipole moment for the electrons, even in the quantum and relativistic regime, in the quantum mechanical picture, is given exactly by the same expression, but you need to have a coefficient at the front of these, which you will get it from quantum electrodynamics, and this G is given by 2.00 something, 1, approximately. Okay? So indeed, the dipole moment that you will get it due to the electron is essentially given by that angular momentum that you are expecting. Okay, so in even the electrons that they are moving, if you assume that electrons are really particle like that moving around, then they have a dipole moment of m. So that electron has a dipole moment of m that is moving around. Is that clear? Okay. And we link this to the spin angular momentum of electrons. So this is what I mean, that m due to the spin will be G divided by 2 E divided by M of the spin that you will get it for the electron. Good. And this G, as I said, that it's coming from the quantum electrodynamics, and you have to do the proper calculation to obtain that. So from the field theory also, you can do the calculation, you can obtain that. Fantastic. Perfect. I think we are right now good, and we can go to the material and understanding how we can, because so far when we talk, we just considered that we have vacuum and there are charges that they are moving around, or we have a certain current densities in space. And due to these certain current densities, we can get a vector potential, and from vector potential, we can get a magnetic field or magnetic flux density. But what is happening if I assume that I have a single atom in space? I'm doing the same trick as 2 lectures ago, which we did it for electric field as well. So assuming that you have an atom, by the way, I'm making that atom in a really strange way. I assume that the electrons are just particles there, and nucleus also there are particles there. So assuming that we have n atoms around, all of those n atoms in space, with a certain let's say densities, and the number of them, they are Avogadro's numbers, so there are many of them, so they are from 1 to, I don't know, n number. And then we are looking at the magnetic field, or let's say the vector potential due to them in a given place. And I know that I have to do 3 coordinates, or I have to assume 3 situations. Let me write it down. So one going to the rest frame of the atom. And from the rest frame of the atom, I have to look at the electrons that they are moving around, which you go to the xi. And from the xi, you will go to the coordinate of x prime I. And then you look at the potential that you are creating here at location of x. You remember that we have done that for the electric potential. Do you recall that? So we had 3, which is 3 points, which was x minus xi minus x prime I. And we assume that x prime I is way, way smaller to the xi, and we do the expansions and doing all of those calculations. And finally, what we obtain that there it was a scalar potential, and here what we obtain is a vector potential. That vector potential indeed will be given by mu0 divided by 4 pi integral of j of x prime plus curl, the curl of magnetization, which is the dipole moment that we do have for those atoms or individuals, x prime, divided by x minus x prime, the 3 of x prime. I did not do the calculation because this now looks like the green term that goes back to the first lecture. It's just 2 lectures ago that we did exactly the same expression and the same expansions. And you will get the dipole moment term, and you have to keep them together, and you will get the current as well. Okay, so we get this expression, and we call this term current due to magnetization. Okay. And usually people also, they call it with the Jm, which is curl of m of x prime. So previously, without material, without having a material, indeed, we had only that term, which was j divided by x minus x prime. And now, in the presence of material, it seems that we have another contribution, which is that look like a dipole moment contribution, which is appearing in the mathematics. And it seems that the form that we do have is look like this. It's given by the curl of the magnetization. And the curl of magnetization is look like, you know, as we discussed previously, the magnetic dipole moment is a vector. Of course, it's coming from the fact that you may have a loop of a current. And now, if you have so many dipole moments all close together, like bunch of them to close together, then if you look at the total currents that you may have, the current here and those magnetic dipole, they are all oriented in the same way. This is what I'm expecting, that the currents are the same. All of them, they are counterclockwise. So between each two individuals, each places here, the current here is like this, but the current on the other side is like that. So they are canceling out between. So any places here, the current is 0, except the edges, which they will be look like a current there. And this total current is given by the curve of magnetization, right? Because that's the effect of the curve, which can be calculated based on the Stokes theorem. Okay, so if you have this material indeed, then you are expecting to create a new current, which is coming from the magnetization of those elements. I mean, you can assign a current to that, a current density there. So therefore, previously what we had curl of B is equal to mu 0 J, and in the presence of material, we don't have only single J due to the free currents, but we do have another term which is coming from the magnetization current. Okay, so indeed that will be mu 0 times J plus curl of M. All right, and then I can just simplify that. That will be curl of B. Sorry. Oh, whoa! What I have done? Okay. B minus M what happened? I cannot write, guys. Oh. Okay. Minus M divided by mu 0 equal to mu 0 J. All right. So it seems that these magnetization or magnetic dipole moments, they will play a role in the field around it, and then we get a new expression, which we call this term H. Indeed, and H is essentially, we call it magnetic field. Previously, remember that was magnetic induction or magnetic flux density. So then we do have curl of H is equal to mu 0 J. I think the unit is a little bit wrong, so let me, oh yes, sorry, my bad. We need to divide it by mu 0, then you will get mu 0. Now that's correct. So indeed, H is defined as B divided by mu 0 minus M. Okay? That's a magnetic field. So Maxwell equation, indeed, or let's say the equation for the magnetic field and electric field inside of the material can be revised as divergence of B is equal to 0 and curl of H is given by J. And if you remember previously what we had, divergence of D was given by rho. Remember that is a free charges. and then we had curl of E equal to 0. That was in the presence of materials. And remember, that is electric and magnetic, which they are not time dependent, so they are time independent. Okay, so where they are time independent, we get these expressions indeed. Good. Previously, we assumed that we are dealing with a linear material, so D was given by epsilon E. Here, the same way, we can deal with linear material again, linear magnetic material. So H is given by B divided by mu, which is the permeability of the material that you have. So is there any question, by the way, guys? And inside of material, remember that H indeed is a function of magnetic field. At the same fashion that we had, the D essentially is given by function of E. And we assume that we have linear, or we have birefringent, or you have, let's say, anisotropic materials, and even nonlinear material. And the same story will happen for the magnetic field. However, we have three kind of materials in terms of magnetic response that we have to be very careful. Okay, so ferromagnetic, which is the one that we have to handle it properly, and the rest they are okay. So the rest is even they are so weak that we can assume that the property that they have is look like very close to vacuum. Okay, and one thing that we don't have in the electric field case, or displacement vector and the magnetic field exists, is what we call it the memory. So materials in terms of magnetic field, they have a memory. So if you apply a magnetic field, it seems that that value will define what is happening for the future of that material. So this is what we call a hysteresis as well. So if you apply a magnetic field and you are measuring, let's say that you are applying the magnetic field and you are measuring the magnetic flux density, and you are looking at the H inside of the material, then you will see that it usually goes on a curve. Okay, so it doesn't go on the same place. Usually you have a hysteresis in the system. That is very quick that I want to just tell you. I don't want to go into really deep discussion and deep calculation about that. So now for materials, as we discussed, we have this expression divergence of B, which is 0, and we have curl of H, which is equal to J. And of course, we can assume that we have two materials. One of them is material number 2, the other one is material number 1. And you may even have a current at the surface of this area, this region. So assuming that you have a surface which is distinguishing the two regions. That's a surface, by the way. I'm trying my best. And material number 2 is here, and the material number 1 is in the lower part. Okay. And here there are current which they are going, so you have K as a current there. So is that clear, the question that I'm defining? Perfect. So this material has mu2 and this material has a mu1, and of course remember that can have epsilon1 and epsilon2 as the electric constant as well. So now we are discussing about the boundary condition that we have to write for in order to understand the physics here. So from the divergence of B, indeed, if you apply the Gauss theorem, which is 0, and assuming let's say a cylinder which is coming from one side and going to the other side, and if you apply the Gauss theorem there, what you will get that B1n is equal to B2n. So normal of the magnetic field is continuous there. Okay. Good. Remember previously for electric field what we had? Let me just move that one somewhere else. For electric field, what we had, it was D1n, D2n minus D1n was given by sigma dot n, which sigma was the charge density at the surface. Oh. Okay. Do you remember that? Good. Okay. So, and that was obtained from the divergence of D is equal to rho, by the way. And here, from the curl of H equal to J, what we are obtaining that H2T, or let's write it in this way, H2 minus H1 cross product of N is equal to K cross N cross H2 minus H1 is given by the current surface current. And the same way, you have to apply the Stokes theorem here. So you will do the calculation of curl of H ds curl of H dv equal to J d3x. You apply for a volume and you do the integration. And from this, you will obtain what, and you have to use the Stokes theorem for the other side, and you will get exactly that expression. For the electric field, however, for electric field, what we obtain that we have to use the curl of E equal to 0. And for the electric field, we obtain that E1t minus E2t is equal to 0. Or what we had was N cross E2 minus E1 is equal to 0. And that was for the electric field. So the boundary conditions now are very clear. If we assume that the material is linear, if the material is linear, which means that H2 is equal to 1 divided by mu to B, and H1 also are 1 divided by mu 1 B1. Then also what we are obtaining here is B1 N is equal to B2N. And we obtain that N multiplied by B2 divided by mu2 minus B1 divided by mu1 is equal to K, which is the surface current density. Even if there is no surface current density in the case of k equal to 0, then we obtain the following expression, which is b1n equal to b2n, and that will be b2t divided by mu2 is equal to b1t divided by mu1. Is that clear? So we have a tangent, or we have a normal vector, a normal component of the vectors. We will see that the normal of the magnetic flux density is continuous, but the tangent is changing based on mu1 and mu2. Okay. If the materials, they have the similar magnetic response, then mu2 divided by mu1 is almost equal to 1. Then it seems that both components of the magnetic flux density, they are continuous there. Good. Okay. Is there any question? No? Okay. So now we will consider a few examples to solve specific boundary conditions. So let's say how to tackle problems for materials that they have certain magnetization. Because remember that J of magnetization was curl of M, and that is important because that will give you the contribution from the material, which they may produce a current-like effect that they will affect the magnetic field indeed in your problem. So how we are solving different problems. So the first thing is that, okay, let's go back. Let's deal with the equations that we are having. So the divergence of B is equal to 0. And from the other side, we know that curl of H is equal to J, which is free current densities. H indeed is, for a linear medium, can be written as a B divided by mu, but in general, it's really, really complicated functionality, which is function of B. Indeed, as you remember, it looked like the displacement vector that can be very, very complicated. It can be nonlinear effect, can be linear effect, or so complicated situation. This is the easiest way, which we assume that is simply given by a scalar, or 1 divided by a scalar, multiplied by the magnetic flux density. Okay? But it can be very complicated. How we solve the problem indeed? I mean, no one really go and do the calculation based on B and H. They have to go with the vector potential indeed. So, and we want to understand how to deal with the vector potential. First of all, divergence of B is equal to 0. That will guarantee that always we have a potential which we can drive the magnetic field from it, which this potential is A, and B is given by curl of A. What freedom do we have about this potential? Or what kind of freedom do we have for this potential? Okay. Do you remember for the other one we had the freedom for the scalar potential? We could add any constant there. Let's look at this. So magnetic field is the physical quantity that we can measure in the laboratory. What I can add to this scalar, to this vector potential, that magnetic field is not changing. I can change this to any A plus any gradient of I. Curl of a gradient is 0, right? So I'm sure that if I change A to any A plus curl of A, gradient of A, both of them, they will give me the same magnetic field. Good. So that is the freedom that I do have. Okay. And that defines what's going on. So A can change to any A plus gradient of chi. Fantastic. So I understand my freedom now, which I can play with it. But still, I know that B still is given by curl of A. Fantastic. And I know that for any material, curl of H is given by J of F. Yes, J of free. And in principle, H is a function of B, which means that is a function of curl of A. So this differential equation now will be given by a function of H, which H vector, which is a function of curl of A equal to J of free charges. So I have to solve these expressions, which is extremely, extremely difficult. Because indeed, that can be, as I say, that can be a nonlinear term. And these nonlinear terms, they will be also expanded in terms of curl of A. So you have to do that expansion. So it can be ended up with, let's say, third order differential equation or fourth order differential equation, etc. So it gets very, very complicated indeed. But simple scenario is that H is a linear function of B. So it means that it's 1 divided by mu B. So let's do this replacement for a linear homogeneous material. Then I do have curl of 1 divided by mu of B equal to J free, which means that that will be curl of B equal to JF mu J of free. Good. Remember previously what I say that indeed H is a function of B and B is a function of curl of A. And now I have to do the same scenario. So B is indeed curl of A. So replacing here, I get curl of A equal to mu J free. So therefore, I will get gradient of divergence of A minus Laplacian of A equal to mu J free. Good. So with the freedom that I had for A, I can choose divergence of A to be 0. That was the column gauge that we just discussed. So indeed, that expression in the column gauge will be Laplacian of A equal to minus mu J of free. What is the solution for this if the currents are localized somewhere? I just drive that, right? So if the currents or current density are localized, then using the Green theorem, we prove that A of x is given by mu divided by 4 pi integral of J of x prime d3 of x prime divided by x minus x prime. The only changes that happens is that with respect to vacuum, mu 0 should be replaced by mu. That's the only thing. And remember, of course, if you have a boundary condition, you have to remember that that terms of boundary condition also appears here. But all of them, they have a coefficient at the front. Okay? Clear? I'm reviewing it, guys. First of all, is magnetostatic. Means that currents, they are not time dependent. Okay? Remember this. Current and charges, they are not time dependent. If they are time dependent, is a different issue. We have to handle that in a completely different perspective. They are not time dependent. Okay, fantastic. Then what I will get that expression, which is curl of H is equal to J. From the Gauss theorem, I will get that B is given by the curl of a scalar, a vector potential. If the material is linear or has a linear response to the magnetic field, then I can do the expansions. In the Coulomb gauge, I will get that expression if the charges are localized or the currents are localized. If the currents are not localized, then I have to do the proper boundary condition solution, which is again Dirichlet, Neumann, or Cauchy boundary condition. Now I consider another case, which is assuming that I have materials, but I don't have a current. That's a second scenario. This is an example. I may have, I don't know, a glass, or I don't know, plastics, or metals, or let's say, I don't know, lithium niobide, which there is no current inside. So JF is 0. When J is 0, then still I have divergence of B is equal to 0. And still I have curl of H is equal to 0. Now, because it doesn't exist. Okay, or J is 0. So how do you solve this problem? Your problem will be reduced to Laplacian of A equal to 0. The same way for a linear medium. Now you are not doing with a vector Poisson equation, you are dealing with a Laplace equation. But it's a little bit strange because I cannot solve that easily. For this specific case, we will use that expression. Curl of H is equal to 0. So if the curl of H is equal to 0, what I can say that will be 1 divided by mu curl of B is equal to 0 for a linear medium, which means that curl of B is equal to 0. Okay? Is that correct? It reminded you of something, right? Do you remember that we had curl of E was 0? What we define from this? E is given by minus gradient of phi. Here, in the same fashion, I can define that H is given by minus gradient of a potential, which I call it scalar magnetic potential. Okay? Is a scalar magnetic potential. If I do have that, then divergence of B is equal to 0, which means that for a linear medium, divergence of H also is equal to 0. So it means that that will be reduced to the Laplacian of phi m is equal to 0. Good. Do you know how to solve these? We spend several lectures on solving only these. All right. Beautiful. So that was another case. But even we can do something more smart here. Because here what I'm missing is how to link to materials property. Okay, divergence of B is 0, no doubt. Do you remember the relationship between H and B in terms of magnetization, not in terms of mu, in terms of magnetization? H was defined as B divided by mu 0 minus the magnetization. Do you remember that? We just defined that. B is H is B divided by mu 0 minus m. So indeed, B is given mu 0 H minus mu 0 m. Replacing inside of that equation, then I will get divergence of mu 0 H. That should be plus, by the way. Plus mu 0 m is equal to 0. All right. And from here, what I will get, mu 0 goes away, so I will get divergence of H is equal to minus divergence of m. True? Good. So that is the expression that I found. Remember that we are solving this problem under the category of J free is equal to 0, so means that curl of H still is 0, which means that H is given by minus gradient of phi m. Replacing inside of that, we will get minus Laplacian of phi m is equal to minus divergence of m. So that will be Laplacian of phi m is equal to divergence of m. Okay. Good. Previously, from the Gauss theorem for electrostatic, what we had, which was Laplacian of phi is equal to minus rho, if you remember, rho divided by epsilon 0, which we had. So it seems that for magnetic field, also, if there is no current density, we will get exactly similar expression. The only difference is that here we are dealing with the divergence of m, divergence of magnetization. So I will define this as magnetic current. Magnetic charge density. I have to be very careful. I will put it in a quote because it doesn't exist. We don't have a magnetic charges. And I will show it with a negative sign. So I will write it as minus divergence of m, and I will call this rho of m. So indeed, when j is equal to 0, then I can solve Laplacian of m minus rho m, which rho m is equal to minus divergence of magnetization. What are the solution to this, guys? Phi m is equal to 1 divided by 4 pi integral of rho m divided by x minus x prime d3 of x prime. This is the way that we solve the scalar potential entirely. All right. There is no epsilon naught because here is rho m, is not rho divided by epsilon 0. And we can just simply replace the expression that we had for rho m, and that will be 1 divided by 4 pi integral of minus divergence of m divided by x minus x prime d3 of x prime. Okay, again, I'm emphasizing this happens when you have materials, right? You don't have a current. Then mathematically, you can define a charge distribution, not a current distribution, which this charge distribution is given by minus divergence of m, the magnetization. Okay, we can use the same analog that we had it for electric potential and finding what we call it magnetic scalar potential. And mathematically, we can find phi m, and from phi m, we can find what is going on with h, which is given by minus gradient of phi m. Okay. It's just mathematical tools, right? Nothing really. This phi m has no meaning, essentially. Some people, they may say to me as well, A also doesn't have a meaning, right? I have to be very careful when it comes to Aharonov bomb effect. A has also meaning, which affects the physical system. Okay, so we are almost done. As an example, I can give you a problem which you have already solved, assuming that you have a sphere, which this sphere has a radius of a, guys, and has a certain magnetization of m. This magnetization m is given by m0 along a specific direction. So I assume that this is the z direction. Remember, that's a sphere along z direction, so that m is given by this. I'm asking you find phi m everywhere. Can you calculate this? I have a sphere with the magnetization of m0 along z. I'm asking you find the magnetization everywhere. Can you do that? It looks like the problem that we solved, that we have a dipole, a sphere with a dipole moment of p along specific direction, and we want to find what's going on with the potential everywhere. So the first thing that you have to do is solving that problem, which is Laplacian of phi m equal to minus divergence of m. Can you do the calculation and find the divergence of m? Of course, I can do the calculation and finding the divergence of m. As soon as you did the calculation of divergence m, then you do the multiple expansions. You say that the phi m are the solutions in spherical coordinates. What you are expecting, 1 divided by r, right? Summation of L from 0 to infinity. AL r power of L plus BL divided by r power of L plus 1, then PL cosine of theta. This is the way that you will solve the problem. The only things that you need to do is finding what's going on with AL and BL based on the boundary condition here. Okay, I will leave this for you as an exercise to do that, because we have already done that several times, and you can find the solution for this problem. Okay, so we are done with this lecture, and the next lecture, as I say, it will be on 27th, and it will be on relativistic regime. So I will stop the recording